In this section of our carbonate diagenesis course, we're going to look at hypogene or bathyphreatic karst. And as the name suggests, this is a form of karst which forms well below the water table, from depths of a few meters to hundreds of meters up to even 8 kilometers below the water table. It's a form of burial or mesogenetic karst. We'll look at it in 3 video chapters. In this first chapter, we'll look at the hypogene process and the type of fluids that create hypogene cavities in the subsurface. In the next, we'll look at the indications in terms of morphology and texturing within the hypogene cavities. And in the third and final video chapter, we'll look at the economic implications of the formation of hypogene karst, both in terms of base metal MVTs, Mississippi Valley type deposits, and also in terms of some types of deep formed porosity in hydrocarbon reservoirs. What is this process of hypogene karstification or hypogene speleogenesis? Well, in a recent paper by Klimchouk in 2022, he described hypogene speleogenesis as the formation of a dissolution-enlarged permeability structure, a void-conduit system, which is formed by upwelling fluids being recharged from below. Those fluids can originate from distant sources, they can be focused or estranged by low-permeability units, or internal sources, such as thermochemical sulphate reduction in buried anhydrite and gypsum units. In all of these cases, the fluids are independent of recharge from overlying or immediately adjacent landscapes. The epigene processes are not part of this hypogene karst formation process. That's inherent in the name. Hypo from the Greek means under or below, and gene, formation. The deepest known active hypogene karst has been identified as something like 6 to 8 kilometers, actively forming in the Tarim Basin in China. So what are the fluids that create hypogene karstification? Well, the 2 main fluids that create hypogene karst are hydrogen sulfide and carbon dioxide. The hydrogen sulfide, when it encounters oxygenated waters, creates sulfuric acid. It's this leaching process from sulfuric acid that creates these characteristic gypsum associations as we free up calcium and sulphate into that leaching limestone solution. We can also see here inherent to that process is the formation of carbon dioxide. Carbon dioxide can also come from deeper hypogene depths, as well as by degassing of CO2-rich fluids near the water table. In terms of where they form, most of the H2S comes from sedimentary basins where a petroleum system is bordering a carbonate upland and we have escaping basinal waters moving up into that carbonate borderland. Or we can have deep sulphate evaporites, anhydrite or gypsum, which are interbedded with the carbonate host, and via the processes of sulphate reduction, either bacteriogenic or thermochemical sulphate reduction, we form H2S. These processes, the formation of H2S and the formation of CO2, are the main agents that are driving the formation of acidic solutions that are leaching to create hypogene karst. One of the characteristic features of hypogene karst, where we have these ascending anoxic deep-seated H2S sources, is that as they reach the more oxygenated groundwaters, or even into a cave atmosphere, the H2S is oxidized to form quite aggressive sulfuric acid, and that rapidly dissolves the carbonate rock. But because of the enrichment of calcium and sulfate in the residual waters, we get mesogenetic gypsum forming as a key indicator of hypogene processes. In terms of CO2, we can have deep-seated endogenic CO2, and we can also have CO2 released during that sulfuric acid genesis reaction. So CO2 comes from 2 sources: deep-seated CO2, often from catagenic processes, and CO2 that's released as part of the formation of sulfuric acid. The key thing with that sulfuric acid reaction is that most of those cave systems formed from sulfuric acid speleogenesis will contain significant volumes of hypogene or bathyphreatic or burial gypsum coming from that oxidation of H2S and the dissolution of the limestone. This schematic by Klimchouk is showing you these processes are coming from depth. So we tend to form fissures feeding up into the hypogene system. And that hypogene system can be at the current water table, or it can be a mixing zone, a phreatic mixing zone at greater depths. As that H2S oxidizes to sulfuric acid, we form hypogene gypsum. These fissure-related systems have a very characteristic morphology. We can see it quite clearly in this image from Klimchouk in 2022, where we can see the fissure control Then we can see the honeycomb leaching into the adjacent limestone related to that sulfuric acid leaching coming up that fissure-controlled hypogene cavern. Quite different in terms of process from the epigenetic features, which forms caves much higher in the hydrology. Often one of the features that we see in hypogene cavern system is that with ongoing uplift, the hypogene cavern features are overprinted as we approach the landscape by epigenetic or surface-derived processes, typical karst-forming processes from meteoric waters that we discussed in earlier video chapters in this module on carbonate diagenesis. The various sources of these bathyphreatic or deeply derived acids are H2S, which can come from thermochemical sulphate reduction at depth, and this is often in association with sulphate evaporites. We can have maturation of organic matter, forming catagenic oil-filled gases that include CO2, H2S, and also some weakly acidic fluids, carboxylic acids, that form during late diagenetic and early catagenic stages of thermal maturation via thermal alteration of kerogen, and to a lesser extent via the oxidation of some existing hydrocarbons. This figure on the right is showing the classic vitrinite-derived scale, where we see shallower, biologically influenced biodegradation processes. We can form CO2, we can form H2S via bacterial processes, bacterial sulfate reduction. Then as we reach the onset of oil generation, temperatures approaching 100, 120 degrees, we form oil, we form hydrocarbon gases, and then at greater depths with degradation, thermochemical associations, and endogenic CO2 formation, we can form H2S and CO2-rich waters at much greater depths. There's also thermal effects. Because of carbonate's retrograde solubility, as we have hot rising CO2-rich hydrothermal waters, as we discussed earlier in our module on carbonate chemistry, that hydrothermal water becomes undersaturated because it's a retrograde system as it cools. We can also have magmatic, volcanic, and mantle-derived sources of CO2. We'll see examples of that when we look at the Brooks of Turkey. When we have magmatic sources, we may see other forms of acid creating hypogene karst, such as hydrochloric acid and hydrofluoric acid in waters associated with deep magmatic sources. We can form at depth below the water table where we have mixing corrosion of two waters that are saturated under different conditions coming together to form undersaturated conditions, as in our discussion of meteoric diagenesis. There we focused on the coastal zone where we had a mixing of meteoric phreatic and marine phreatic waters. But this can also occur in deeper settings, in bathyphreatic settings, where we have mixing of two waters. We can also have situations where we have deprotonation of clays creating acidic conditions, as we discussed in the evaporites course when we looked at the pre-salt formation of stevensite in the Aptian evaporite-associated carbonates of offshore Brazil. There are multiple sources for the acids which can create leaching of limestone at depth, independent of surface-driven processes. Pressure is another one. Pressure increases will put CO2 into solution, and that will also create increasing levels of carbonic acid. This leaching process with a number of different acidic sources tend to create characteristic honeycomb or spongiform karst. Here we can see it in Lechuguilla cavern in Texas, sometimes called the Boneyard Maze in this particular example, where we have a central area of irregular rooms with local gypsiferous maze caves where we see intersecting fissures and sponge-like solution products, locally known in the Lechuguilla region as punk rock, and also sparse outlet passages leading to active or relic springs. The key thing is that this process is fissure controlled. It comes out of the fissure or the fracture system, which is allowing those upwelling waters to enter the limestones. Some of these caves only have a single passage. Then from these main zones of cave development, these fissures, they typically narrow downwards and they widen upwards with this spongiform margin to a lot of these active hypogene systems. In active examples, as we'll look at in the next video chapter, we see these fissures passing into fractures or joints that are the main inlet zones for this H2S and CO2-rich water coming from depth. Typically, these systems are leaching upwards, and so we'll see the ceilings of the major cave rooms smoothed and arched with a classic cupola. We'll also see a lot of evidence of gypsum formation and replacement, either as gypsum rinds or gypsum-floored ponds. Increasingly, we're recognizing hypogene karst systems from around the world, and here are some examples in different locations. In Australia, caves like the Jenolan Caves, In Europe, like the Fossati caves in Italy, or in the gypsum maze caves of Ukraine, the El Balazia caves in Egypt in the Nile Valley, which were acid hydrologies tied to the Oligomycene opening of the Red Sea Rift. In Mexico, one of the classic examples we'll look at in the next chapter, where we see active cavern hydrology forming today in an H2S-rich environment, which is accessible. And then we have classic cave systems such as Toca de Boa Vista caves in the Ediacaran Dolomites, in what is probably the longest hypogene cave system in South America. And then we have these very well-studied hypogene provinces, which we'll look at in the next chapter in detail, in the Guadalupes, and also in the Black Hills, where we see typical hypogene features, cupolas, fissure-controlled passages associated with gypsum formation. Klimchouk showed us that there is a characteristic set of morphologies that differentiate hypogene-formed cave systems from the more typical meteorically influenced epigene processes that we've discussed in 2 or 3 sections earlier in this module, where we looked at meteoric epigene processes. What differentiates hypogene cavern systems is that they have a feeder system coming from depth, and very often they have a keyhole shape in their early forms that expand laterally into the limestone to form that inverted funnel shape with a rising chain of dissolution cupolas at the head of that cavity. Quite often they're focused between an upper aquifer and a lower aquifer with a confining bed within. And then we see this rising chain of cupolas or sealing half tubes moving up through the systems. This association of cupolas, a keyhole-shaped master passage, is indicative of these hypogene caves. So let's have a look at a few examples now of hypogene caves to illustrate this process of fluid rising from below and leaching into fissure-controlled rising cavities as those acidic waters ascend from depth. Here's the Jenolan Caves in the eastern of Australia. We see a typical hypogene fissure, no ornamentation on the walls, but there has been later access by epigene ornamentation, the typical stalactites hanging from the ceiling. The hypogene episode is indicated by hypogene cave floors, which are carboniferous in age. So this is a long-term process, and this is quite typical of many hypogene systems. They've been forming for millions and even tens of millions of years at depth before they break out at the surface and transition into epigenic or epigene cavity systems. Here's a cupola, one of these cup-shaped roofs to a hypogene cavity, but it's clearly then broken out into the surface-fed system. So we see the typical stalactite-stalagmite association overprinting that cupola shape once it's broken out into the active meteoric phreatic system. Then we have the Monoyaus cave beneath Budapest in Hungary, which is an actively growing hydrothermal system. And those waters are at about 27 degrees in the upper parts of these hypogene water-filled cavities. Notice the lack of surface ornamentation on these leaching systems. We don't see evidence of any ornamentation associated with leachings from these hydrothermal waters. You actually have hypogene systems forming not just in limestones, but also in gypsum. So in the Optimist cave system of Ukraine, which is the world's largest, longest gypsum cave, we see a massive multi-level labyrinth in a gypsum host that stretches for more than 260 kilometres. We see that typical fissure-controlled cavity with the current water table off in the distance. Once we get these systems up into the vadose environment, we see gypsiferous nodules and helicites forming. We can also have systems where we have rising hypogene or hydrothermal pipes breaking out to the surface. These are the brooks, these massive hypogene collapse chimneys that break out magmatic CO2-rich waters, breaking through the neogene in Suyu limestone in Turkey. This system has now been aggravated by the lowering of the water table by groundwater extraction for agricultural purposes. We have a whole series of reactivated obbrooks daylighting overnight, such as Obrook Enoba, the lower image, which daylighted in the winter of 2008. Here's the Toca de Boa Vista cavern in the Ediacaran Salitre Dolomites, part of the Toca de Barajuda system, which at 114 kilometres in length is the longest cave system in South America. The smooth-walled stretches once again been overprinted by later epigene-formed stalactites and stalagmites. This system is also interesting in that we can see the preserved water table, now drained, indicated by the outgrowths on those fused stalactite-stalagmites. And lastly, another well-studied hypogene system are the early stages of Wind Cave in South Dakota, which contains excellent examples of what were hypogene leaching of the wall rock by sulfuric acid solutions, forming these very characteristic calcite vein veils hanging from the ceiling, where we've leached the intervening matrix and just the calcite in the veins remains, and also that very characteristic boxwork texture associated with the Wind Cave hypogene stage. In the next section, we'll look at detailed indications of the hypogene origin of these cavities.